This lecture is part of a series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. The fifth lecture, MRI Imperfections Part 1, is broken down into three parts. Lecture-05C covers Maxwell Fields. The learning objectives for this lecture include being able to appreciate the Maxwell fields are unavoidable, understand the spatial variation and direction of Maxwell fields, describe the MRI hardware specifications that impact Maxwell field amplitudes, and list two or more methods to correct Maxwell fields. We've used this slide several times now to describe the B-field assumptions in MRI. In particular, on the bottom, we describe three assumptions for gradient fields, including that they are perfectly linear and temporally modulated exactly as specified, which we'd covered in the previous two lectures. In this lecture, we'll address Maxwell fields, and in the simplest case, we assume there are no Maxwell fields, but in fact, the Maxwell fields do generate important magnetic field components that contribute or corrupt the imaging process. When gradient fields are applied, other fields are unavoidably produced as described by Maxwell's equations. They're generated concurrently with the applied gradient and do so instantaneously, and they don't persist unless the gradient is active. They produce magnetic field components that are perpendicular to the B0 direction, and they introduce higher order spatial dependence. And the Maxwell fields are also known as concomitant fields, so in the literature you'll hear both of these terms used. The first law that concerns us is Gauss's law for magnetism, which states that there is no magnetic monopoles, or that the magnetic flux through a closed surface is zero. This governs the magnetic fields that exist when one particular magnetic field gradient is produced. The other Maxwell equation that concerns us is Ampere's circuital law, which states that magnetic fields can be generated by changing electric fields. We'll examine both of these laws more carefully to better understand the origins of Maxwell fields in magnetic resonance imaging. In the first equation, we can see that it's the sum of three different gradient terms. And in fact, the third term is precisely the Z gradient term that we use actively in magnetic resonance imaging. It's a magnetic field change of the Z B field changing in the Z direction. These other two components represent magnetic field gradients of the Bx component changing with X and the By component changing with Y. And we don't actively generate nor manipulate these magnetic fields in magnetic resonance imaging. On the right-hand side, if we expand Ampere's circuital law, we get three equations. And these equations describe the interdependence of various magnetic field gradients. And again, we can identify that two of these terms represent the Gy gradient, that is, the Bz component of the field changing with Y, and the Gx gradient, that is, the Bz field changing with X. So these three magnetic field gradients are the ones that we control actively in MR, Gx, Gy, Gz, but necessarily, as a consequence of these equations here, they give rise to the production of other magnetic fields. And those magnetic fields are active and exist only during the application of our externally applied magnetic field gradients. The active generation of the gradients, the Gx, Gy, Gz gradients, necessarily generates additional B-field components or B-field gradients. So let's look at one of these terms in particular, and we'll examine what happens during the application of a Gx gradient. To orient you, our coordinate system is as follows. This is the Z direction. The Z direction will point along the long axis of the scanner, and then we have the X direction, which typically points left-right in the scanner. We can examine what happens precisely at isocenter, and here the vector lengths indicate the magnitude and direction of a magnetic field. So the B0 field we know to be Z direction, Z directed, and large, that is, and therefore represented by a long vector. If we apply a Gx gradient and we're at isocenter, because our X position would be 0, the magnetic field contribution from that gradient is quite small, or in fact 0. If we move along the z direction, so now we go to a position that's isocenter plus z, so we've moved along z, we still have our B0 field, which is large in magnitude and points directly in the z direction. And we have a gx component, but because this is a gx gradient, the gx gradient component when dotted with x is still very small, or in fact 0. So those are two uninteresting cases. Now, just to remind us of what happens when we play gx gradients, we should move in the x direction. And if we move along the x direction, so now we're at isocenter plus some x, we still have our constant B0 vector, and now we've added a meaningful gx gradient component. So x being substantially non-zero, we have a significant B field component that arises during the application of gx. Now these aren't to scale, but they're just to be representative of what's happening. And then lastly, we can move out to a position that's isocenter plus x plus z, and here we see that in fact we just get the same magnetic field components because having moved in z doesn't increase the field contribution from an x gradient. So if these vector diagrams don't make sense, you might review carefully, again, pause the video and go back, because they're important to understand as we move towards an understanding of Maxwell fields. So now let's examine exactly that, Maxwell fields. We have to, anytime we're playing an x gradient, it means that there will also be an equally produced x component, the B field, in the z direction, or as a function of z. So again, we start at isocenter. We have our main B0 field, and the action of a gx gradient produces no meaningful field from the gx component, and if this field is 0, then the concomitant field will also be 0. We can move out in the z direction. As we move out in the z direction, we have the gradient producing no meaningful field, and so then there's no meaningful concomitant field either. Now, of course, the more interesting case finally arises, where here we're at isocenter plus an x position. The B0 field is still persistent, and the gx gradient contributes, of course, a BZ component to our magnetic field, but necessarily gives rise to a BX component to our field as well. And that BX component has a gradient in the z direction. And that means that as we go further into the z direction, so now isocenter plus x plus z, this BZ component has in fact gotten larger. So here we can gain some insight as to the spatial dependence and gradient field dependence of these so-called Maxwell field terms or concomitant field terms. Okay, so quick quiz. Concomitant fields are highest at isocenter, lowest at isocenter, only parallel to B0, or point in all directions. And the answer is lowest at isocenter. We know that there's no concomitant field contribution precisely at isocenter, and that in fact the concomitant fields are pointing perpendicular to the B0 field and vary as a function of space. So conventional MRI scanners use so-called symmetric gradients, and that means that each gradient's isocenter coincides. If you think of these as being independent or individual hardware components, they have to be lined up carefully so that when currents are coursing through them to produce gradients, the lowest gradient, that is no gradient, for each of the x, y, and z axes is geometrically coincident. The gradients then, the concomitant fields rather, reduce to the following expression, which approximates a second order spatial dependence, that is, when we're using a symmetric gradient coil set. Now the origin of this expression is difficult to arrive at, but the expression itself is not so complicated. What we learn is that for symmetric gradient coil sets, we only have a second order spatial dependent on the B field, and so this is the B concomitant field. This would superpose with any other magnetic fields. And we see that it's inversely proportional to B0, and it depends on the applied gradients through these quadratic expression. And we learn some interesting things here. It's actually inversely proportional to B0, and that means that concomitant fields are more problematic at lower magnetic field strengths. So for 3T or 7T scanners, the concomitant fields can be relatively negligible, but for low field systems, which are getting research attention now, half Tesla systems, for example, these terms are more important. It also depends specifically on the gradient squared, and that means that if you have a high performance gradient system that is achievable, it can achieve high G maxes, then it will be more susceptible to generating larger concomitant fields. And finally, we see that these magnetic fields are always greater than zero, so they're always producing a positive bias from a field perspective. So let's think about the contributions that these concomitant fields make to our imaging system. So the net magnetic field we know now deviates from the z direction or the k hat direction. We have a concomitant field component that pushes the net field off axis, so to speak. So what effect does that have? Well, it turns out to have a negligible effect on polarization. These fields are far too small. They're on the scale of microtesla or maybe millitesla, hundreds of microtesla. Does it have an effect on excitation? No, not really, because the B0 field is still largely perpendicular to B1, which is important for excitation. There are additional field components, but these additional field components contribute to spin phase and frequency, and that's problematic, of course. And they're space and time dependent, and so they lead to geometric and encoding distortion. So concomitant fields are problematic in that they do corrupt the images themselves. There's another expression that we can look at, which is a description of the concomitant field gradients. And this here, although difficult to derive, represents what we call the concomitant gradient tensor. And we'll see here that this is a matrix operator, and it tells us about the gradient deviation as a consequence of concomitant fields, but dependent on the spatial position of interest. And so since this is a tensor, we can multiply it onto a position vector, and for a given position vector, achieve the magnetic field gradient concomitant field component that deviates or offsets us from the target or preferred or desired magnetic field gradients. So here in this last expression here, what I want to make clear is that we generally have a target gradient waveform. These are the trapezoidal gradient waveforms that are designed to meet a specific goal of imaging or pre-phasing or phase encoding or diffusion encoding or whatever. So these are the gradient fields that we program and want to produce. We necessarily produce concomitant gradient fields, and these concomitant gradient fields depend on space, right? And they depend on time in the same way that the applied magnetic field gradient does. And these concomitant gradient fields superpose with the target fields and therefore give us a different gradient trajectory during our pulse sequence. And so this additional component here contributes to, say, phase and frequency encoding, or it may contribute to velocity encoding or something else that we're trying to capture with our imaging system. And so, needless to say, it contributes errors to the overall imaging process. So we can take a simple example here. I'll just start with some code where we describe the field of view, the B0 field being a half Tesla field, and the G max being a high performance 100 millitesla per meter system. And so I've chosen this because it makes more apparent the concomitant field effects, that we have a low field system with high gradient performance. We pick a gradient direction, so we're thinking here in terms of like diffusion encoding directions. That's off axis, and we choose a position, specific positions that are half a field of view away. And if we do so, we can examine the concomitant field gradient contribution as a function of space when we're applying, say, our maximum gradient amplitude. And we can see that we have a spatial variation across the field of view, and that spatial variation is increasing as we go from z equals 0, that is isocenter, to 100 millimeters to 200 millimeters. And so, as expected, the further and further away we get from isocenter, the worse these magnetic field gradient components are. We can similarly look at the components of along the y gradient. So this is a concomitant field gradient y component, and we can see it has a different spatial distribution in its magnitude, but again it's increasing as we go from close to isocenter to 100 millimeters away to 200 millimeters away. And lastly, we can make the plots of the magnetic field gradient contribution, concomitant field gradient contribution, the z component, as we go from isocenter to farther and farther distances away. And it's important to also pay attention to the units, just so that we appreciate the scale of these things. And so here the units are in terms of, as described here, Tesla per meter. So these are very small field contributions relative to our typical magnetic field gradients, which would be, in the many millitesla per meter range. Okay, another quick quiz. So concomitant fields are least important for high field, high Gmax systems, low field, high Gmax systems, high field, low Gmax systems, or low field, low Gmax systems. The answer to this comes from the equations that we were just discussing, and we should identify that the concomitant fields are least important for high field, low Gmax systems. So let's look at concomitant fields as an application of concomitant fields, specifically here in diffusion imaging. We start again with the same conditions that we described before in terms of the B0 field, the gradient maximum, and the directions and so forth. And we just want to calculate a B value to target about 1,000 seconds per millimeter squared. That's a very typical B value used in diffusion imaging. And without getting too concerned about the details, the bottom line is we use some gradient information to calculate a B value and determine the gradient amplitude and durations that will produce the B value of interest. And then we can calculate, of course, the concomitant fields that go with this, and then the actual gradient waveforms. So the gradient waveform that we have in mind is just what we call a bipolar gradient waveform. So it's positive then negative. And the effect of this gradient waveform will be to produce a B value of about 1,000 seconds per millimeter squared. And we're applying that gradient or similar gradient along the x, the y, and the z axes. We can then, using the previous equations, estimate the concomitant field contribution. This would be at a particular position distant from isocenter. And we can see that the field contributions are relatively small. Notice that the scale that these fields are plotted on is an order of magnitude different than the desired or target gradient waveforms. And if we add these together, and we should add them because when we're playing this diffusion encoding gradient, this one is necessarily produced as a consequence of Maxwell's equations, we can see that we get a slightly perturbed gradient waveform, maybe most easily noticed by looking at the very edges of the gradient amplitude relative to the box, just so you can notice some subtle shifts of the gradient waveform. And so while subtle in appearance, they still can contribute significant phase and frequency offsets during imaging, which lead, of course, to errors in the imaging experiment. And so an example of this is in the calculated B value at a position distant from isocenter. And while the target B value was 1,000 along each axis, so 1,000 on the x, y, and z axis, and without the consideration for concomitant field gradients, we would get exactly 1,000. We can see that with the contribution of concomitant field gradients, we're either pushing down or pushing up the B value at a particular position. And so that's problematic. That's for two reasons. One, we're getting a B value, which is not the target B value, and in fact we're getting a B value that's magnetic field gradient dependent. So depending on which direction we're probing, we're getting different B values. And then, as we'll see shortly, it's a little bit worse than that because they also vary over space. And these variations are not to be ignored, right? Meaning that they're large enough to contribute meaningful measurement errors in magnetic resonance imaging, in this case diffusion-weighted imaging. And as MR moves to being an increasingly quantitative field, it's important that all of these corrections be accounted for, or all these errors be corrected for. So let's look again just a little bit more at this concomitant field effect in diffusion imaging. The positions and information for the simulation are shown on the left-hand side here. And here we're just plotting the delta B, so how far off are we in B value as a function of being, at isocenter or further and further away from isocenter. And you'll notice that the patterns here look quite similar between these, but in fact, if you look really carefully, the scales have changed. And so what's being represented here is that the B field offset goes from being something, sort of nominally close to zero to increasingly negative and more negative as we move further and further from isocenter. So worse as you get away from isocenter, and there's patterns across the field of view, all of which need to be accounted for. Similar but different if we look at what happens to the offset to our B value for a Y gradient, and then we get a slightly different pattern and orientation when we look at what happens to the B field offset for the Z gradient and as we move along the Z direction, until we can finally see that these B value offsets are actually quite large relative to the target B value of 1,000. So we can carry this out a little bit further, and we can look specifically at the effects in an object. And so here we've simulated a sort of head-like object that has a few different ADCs. So we use the ADC of fat, white matter, gray matter, and CSF applied, as you can sort of see in this so-called true ADC map. And if we estimate the delta ADC as a consequence of the concomitant fields, we can see that we get a spatially varying distribution of ADC errors for when we're playing the X gradient. We get a similar pattern, although slightly different, of ADC errors as a consequence of playing our Y gradient. And then most notably, we see a pretty substantial error in our ADC map when we're playing our Z gradient. And so again, this is just to demonstrate that these concomitant fields create offsets and spatial gradients in the estimated ADC if they're not corrected for. And so then it's important to think about correction methods for dealing with this. So the correction methods, some are quite simple, and we won't spend a lot of time getting into them, but conceptually it'd be good to appreciate. One of the easiest methods is just so-called waveform symmetry about a 180 refocusing pulse, so that any B fields arising from concomitant terms that produce a phase will simply be refocused. So if we play a gradient before the 180 that produces concomitant fields, those are simply offset by playing the exact same gradient after the 180. You can also use phase subtraction techniques. So this might be a repeated acquisition, so with the gradients turned off or maybe toggled, that is inverted. The downside being that you would have to acquire substantially twice as much information for a phase subtraction approach to be useful. You can also think about interesting waveform design problems here. And so you could shape the gradients in very specific ways to limit the effects of concomitant fields. We saw previously that they depend on the gradient amplitude squared. So you could think of ways to minimize their amplitude while still achieving other targets of your pulse sequence. That may, of course, lengthen your pulse sequence, and so that may be unacceptable for other reasons. But there are other more complicated ways to reshape gradients that can give rise to minimizing concomitant fields, if not getting rid of them. Lastly, of course, there's always further reading. These are some great papers that I would suggest for follow-up on this topic. And of course, the Handbook for MRI Pulse Sequences is a great textbook for reviewing this material. So what about imperfections that arise from object motion and flow? For that topic, you'll have to turn to Lecture 6, where we'll get into the details. Thanks for joining us.